So we're doing real cryptography now, starting on Thursday of last week. And chapter 2 is on discrete logarithms and Diffie-Hellman. So we start off with a little bit of number theory that underlies all the cryptography we're doing and the discrete logarithm problem. So suppose that P be a prime number and let G be a primitive root modulo P. So what does that mean? That means if we look at FP, which is the finite field with P elements, or Z mod PZ, the set of congruence classes mod P. So we can think of the congruence classes as being represented by the first P non-negative integers, 0 up to P minus 1. And FP star is the non-zero elements of FP. So if you throw away 0, that's the set of congruence classes represented by the first P minus 1 positive integers. And you can add and subtract in this field mod P. And we say that it turns out that FP star is what in algebra would be called a cyclic multiplicative group. You don't have to know what these words mean, you just have to hear them, but which means, this is all you need to know, there exists at least one number G in FP star, such that if you take the powers of G, 1, which is G to the 0, G to the first power, G squared, up to G to the P minus 2, these P minus 1 numbers give you every non-zero number mod P. That's what a primitive root is. And so G is what is called a primitive root. So for example, you take P equal to 11, I claim G equal to 11. G equal to is a primitive root. So we calculate the powers of G. So this is everything mod 11 in F11. G to the 0 is 1. Well, G is 2. So 2 to the 0 is 1. 2 to the first power is 2. 2 squared is 3. 2 cubed, 2 to the second power is 4. 2 cubed is 8. 2 to the fourth power is 16, which is the same as 5 mod 11. 2 to the fifth power is 32, which is 10 mod 11. 2 to the sixth is 64, which is 9 mod 11. 2 to the seventh is 128. What is that mod 11? I believe it's 7. 2 to the eighth is 256. If you divide that by 11, what is the remainder? I think it's 3. 2 to the ninth is 512. If you divide that by 11, I think you get 6. 2 to the 10th is 10,024. If you divide that by 11, what do you get? 1. You're back to 1. So if you look at these powers of 2, from the 0th to the 9th power, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get all the powers, you get all the non-zero numbers mod 11. So 2 is a primitive root mod 11. And what is the discrete logarithm? For the prime 11 and the primitive root 2. So the logarithm.
Professor.
Yes.
Yeah, you say G2 is a primitive root?
Yes.
Can you please explain that?
Sorry?
Can you please explain the last statement?
What this means?
Yes, ma'am.
Yeah.
You said before we get to...
So primitive root means the powers of G give you all possible numbers mod FP star. All congruence, all non-zero congruence classes mod P. So if I take P equal to 11, if I start taking the powers of 2, I get, and I reduce the mod 11, I get 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. You look at these numbers, that's every number from 1 to 10. So every non-zero number mod 11 is a power of 2.
Okay. So that means from 1 to 10, you get every number there.
Yes.
Okay. Thank you, sir.
Let's look at another example. Suppose for P equal to 11, I took G equal to 3. What are the powers of 3? 3 to the 0 is 1. 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. Mod 11, that's 5. 3 to the fourth power, which is 81. Mod 11, that's 4. 3 to the fifth power is 243. Mod 11, what is that? It's 1 again. 3 to the sixth power will be 3. 3 to the seventh power will be 9. So if you take the powers of 3, you get 1, 3, 9, 5, and 4, and that's it. So G equal 3 is not a primitive root, because you cannot get every number as a power of 3, mod 11. But you can get every number as a power of 2 mod 11. So 2 is a primitive root.
Okay.
All right. And the discrete logarithm problem says, given a number h, so log h to base g. Right? This means if this is equal to k, this means g to the k is equal to h in your field FP. So here I have my prime 11 and g equal 2. Suppose I want to know, what is the log of 7 with respect to 2? Well, let me choose a different number. This is slightly. What is the log of 5 with respect to 2? Well, it's equal to 4, because 2 to the fourth is 5. What is the log of 9 with respect to the primitive root 2? 2 to the sixth is 9 mod 11. So the log of 9 to base 2 is 6. What is the log of I don't know, 10 mod 11. Someone tell me the answer? What is the discrete logarithm of 10 with respect to the primitive root 2 modulo the prime 11? You just look at this table and look for 10. Here it is, there's 10. 2 to the 5th power is 10. So the power to which you raise 2 in order to get 10 mod 11 is 5. That's the discrete logarithm. Okay. And the important point in cryptography for large prime numbers P, computing the discrete logarithm is a very hard problem. Okay. For a prime like 11, it's easy. But if you have a prime with 1,000 digits, it is no longer easy. It's very hard. And if you take a prime with 100,000 digits, the universe might burn out before you can solve the discrete logarithm problem. So there are two things you have to take away, well, several things you have to take away from this. You must know what is the definition of a primitive root. You must know what is the definition of the discrete logarithm. And for a small prime, if I give you a primitive root, you should be able to calculate the discrete logarithm because it's a very small prime and it's not a huge amount of computation. The discrete logarithm has many of the properties of the usual logarithm. For example, the usual logarithm, so the usual log from pre-calculus says the log of xy is the log of x plus the log of y. Okay? So you use this in calculus all the time. For the discrete log, we have the same identity. The log of a number a to the log of ab to the primitive with respect to a primitive root g is the log of a with respect to g plus the log of b with respect to g. For all ab in fp star. Let's prove this. Proof. Suppose the log of a to the base g is r, and the log of b to the base g is s. So this means that g to the r is equal to a in the field, and g to the s is equal to b in the field. So ab is g to the r, g to the s, which is g to the r plus s, which means the log of ab, the discrete logarithm to base g, is r plus s, which is the log of a to the base g plus the log of b to the base g. So that's a proof of this additive property of the discrete logarithm. It's essentially exactly the same proof you would have done in pre-calculus when you were learning about the logarithm. Okay. So any questions about the log? All right. So now we come to a fundamental problem in cryptography. is called key exchange. So you have Alice and you have Bob, and they want to be able to send secret messages to each other. And in order to send the secret message, there's a certain cryptographic scheme. Everyone knows what this cryptographic method is, but to encrypt and decrypt, you need the key. You need a secret key. So before you can even start the process, there has to be a key that Alice and Bob have. And they can't encrypt the key exactly because they need a way to both come up with the same number. And Bob cannot send the key to Alex, and Alice can't send the key to Bob because the enemy, Eve, is intercepting all their messages. So everything Alice sends to Bob and everything Bob sends to Alice, Eve gets to see. So the problem is, how can Alice and Bob obtain a key that Eve cannot obtain? Right? That is, how's Bob going to send Alice the key? If he sends it the key, Eve will intercept it. She'll know what the key is. Can Bob encrypt the key? Well, they don't have a cryptographic system set up yet. They need a key in order to do their cryptography. Right? So this was for a very long time a very subtle, unsolved problem in cryptography. And then it was solved. It was solved by two people named Diffie and Hellman. And it turns out they weren't the first. There were cryptographers who worked for the British in what's called GCHQ, General Communications Headquarters. It's the British equivalent of the American National Security Agency, NSA. These are the agencies responsible for encryption, decryption of messages. So how can Bob and Alice exchange a key that Eve, even though she's intercepting every message back and forth between them, Eve cannot figure out? So this is called Diffie-Hellman key exchange. So we start with a large prime P, which everybody in the world knows. That's not a secret. And an integer G, which might be a primitive root mod P, or it just might be a number that's not necessarily a primitive root, but when you take its powers, you get a very large number of different congruence classes mod P. So this is public knowledge. This is the whole world knows what is the prime P and what is the primitive root G. Okay, this is not a secret. Okay, so what is the process? Let's start with Alice. Alice chooses a secret integer A. She's never going to tell anyone A is. She knows it. It is never being transmitted. And then she computes G to the power A mod P. And she gets some number A. Right? So Alice picks a secret number A. She's never going to send this to Bob or anyone else. That's her secret number. She takes G to the power A and calls that number capital A. And here's Bob and she sends the letter A to Bob. So Bob gets this number A, and of course, Eve, who intercepts every communication, Eve knows what the number A is, right? Capital A. Now, little a, Alice's secret integer.
Professor.
Yes?
How does Eve know what letter A means?
Sorry?
You say Eve know letter A. How does he get to know
It's a
letter
number. She gets that number.
Eve?
Yeah. Anything that's being transmitted, Eve can intercept and read. So Alice computes this number, capital A. She sends it to Bob.
Yeah.
And Eve intercepts it, and Eve knows what capital A is. Right?
Okay.
She's a spy. She can eavesdrop and get that number. So Eve knows A, capital A. She doesn't know little a.
Okay.
Why doesn't she know little a? Little a is the logarithm of capital A to base G. And the discrete logarithm problem is too hard for anyone to solve. So Eve cannot find little a because she cannot solve the discrete logarithm problem. No one can.
But he knows letter A.
She knows capital A.
Okay.
Okay. Bob chooses a secret number, little b, and he computes G to the power little p mod p. And he calls that number capital B. And Bob sends the number capital B to Alice. And Eve, she's the spy. She's very good. She intercepts, she eavesdrops, she bugs their communication. Eve knows capital A and capital B. Okay? She doesn't know little a or little b, but she knows capital A and capital B.
Okay.
And Bob doesn't know little a, and Alice doesn't know little b. Alice is no different from Eve. Alice knows capital A and capital B, and Bob knows capital A and capital B. Okay? Now, how do they get a key? So Alice computes, she got the number B from Bob. She takes B to the power A. Right? B to the power little a. Alice knows little a. No one else does. But she can take this number, capital B, raise it to the power A mod P. Okay? And she gets some number. Right? So Alice has this number, capital B to the little a. Right? Bob computes the number he got from Alice, capital A, raised to the power little b mod P. Right? Now, notice the spy, the enemy, Eve, cannot do either of these calculations. Eve knows capital A and B. She does not know little a and b. So Eve cannot compute this number, nor can she compute this number. Right? And here is the fundamental fact. B to the A, capital B to the little a, this is the number Alice has, is equal to capital A to the little b. That's the number Bob has. Because capital B to the A, what is capital B? G to the little b raised to the A is G to the AB. And capital A to the B, capital A is G to the little a raised to the power B, is also G to the AB. So these two numbers are the same. Alice has this number and Bob has the same number. And that can be the key that they use in their cryptography. So through public communication, everyone knows the prime P, the primitive root G. Somehow Alice and Bob communicating to each other, they can compute a key which they know, but no one else does, and no one else can find out. Eve has no way of getting this key from a knowledge of capital A and capital B. Right? So what is the problem? The problem is through what is basically a public communication channel for A and B to be, for Alice and Bob to be able to come up with a shared key that they can then use to send secret messages back and forth. And Eve, who's intercepting all communications, cannot figure out what that shared key is. So Alice and Bob have exchanged a key. They end up with the same number, and there's no way Eve can figure it out. Okay. So this is Diffie-Hellman key exchange. This is what we talked about on Thursday, and it's fundamental in cryptography. It's a fundamental idea which is used over and over and over again in many other crypto systems. So calculations are hard, I guess. But let me look at an example that's in the text. This is example 2.7. So suppose Alice and Bob are given or choose the prime P equal to 941. And we're told, and we should believe, that the number 627 is a primitive root mod the prime 941. So if you start raising 627 to powers 1, 2, 3, 4, 5, you will get every congruence class, you'll get every number from 1 to 940. Okay. So Alice, her secret number that she doesn't tell anyone else is going to be 347. And Bob's secret number, which he doesn't tell anyone else, he certainly doesn't tell Alice, is going to be 781. So what is the number capital A that Alice computes? A is going to be G to the A mod P, which is 627 raised to the power 347 modulo 941. Actually, I'm sort of curious. I'm going to open up Maple for a second. Let's see. Let me see if I can share the screen here. Share screen, Maple, share. Okay. So you should see this Maple screen. And the question is, Alice's number A is equal to what? You want to take 627 and raise it to the power of 347. Now, I don't think that Maple can handle a number this big. Oh, it does. Wow. That's that number. What do you know? Okay. But that's not what I want. I want to know what is the remainder when you divide this number by 941. So in Maple, the command to find a remainder is integer remainder, IREM. So I want the integer remainder of this number when I divide by my prime, and my prime was 941. Huh. So according to this, A is 390. So A is 390, right? That's exactly what the book said, and it's correct. Now, Bob chose the secret number 781. So his number, capital B, is G to the B mod P. What is that? That's G 627 raised to the power 781 modulo 941. Let's just see whether Maple will still give me the right answer. Let's see if I can share the screen again. Okay. So now my number B will be the integer remainder when I take 627 and raise it to the power 781 modulo the prime 941. And according to Maple, that's 691. And that's exactly what the book says also. That's always nice. So A is 691, sorry, B is 691 mod 941. So here we have Alice, here we have Bob. What Alice sends to Bob is her number A equal to 390. What Bob sends to Alice is his number B equals 691. And Eve, who intercepts all communications, gets those two numbers, right? So what does Eve know? Eve knows the prime P is 941, the primitive root is 627, and she also knows A and B. So Eve knows these two numbers. She knows the prime and the primitive root. But what is the key going to be? So the shared key, Alice takes the number she got from Bob and raises to her secret number 347. Sorry, and raises it to her secret number mod P, which is 691 raised to her secret number 347 modulo the prime 941. And Bob takes the number he got from Alice and raises it to his secret number B mod P, which is, what was the number he got from Alice? 390. What is his secret number? 781 modulo 941. And these have to be the same. Let's go back to Maple and have Maple do the calculation for us. So let's call it the key. At least the key that Alice calculates is the integer remainder when you take 691 and raise it to the power 347 and divide by 941. $470. Let me call this. That's the key that Alice computes. What is the key that Bob computes? He got the number capital A from Alice, which was 390. His secret number was 781. And he wants the integer remainder when you divide that by 941. So this is the integer remainder when you take, a to the power b. The capital A was 390 raised to Bob's secret number, 781. What do you know? You look, 470, 470. They are the same. So both Alice and Bob now share the secret knowledge, the secret key 470. Right? So in both cases, this is 470. Right? And Eve, there's no way from the numbers 390, 691, the prime p equal 941, the primitive root g equals 627. There's no way Eve can find this number, 470. I mean, she could do it if she could solve the discrete logarithm problem, because she needs to know either little a or little b. But the whole method of cryptography and Diffie-Hellman is based on the fact that the discrete logarithm problem is computationally too difficult to solve. Right? Now, if you're not a computer science major, you might say, of course you can solve the problem. You just run your computer long enough. But if you are a computer science major, you know that running your computer long enough might take 1 billion years. And you need to solve these problems in less than 1 billion years. So what is the key here behind all of these cryptographic methods is the issue in what is called computational complexity, which is a core problem in computer science, theoretical computer science, and mathematics, which is trying to estimate how hard a problem is and how difficult it is to solve. So this is Diffie-Hellman key exchange. Right? Any questions about this? Okay. Now, what Diffie-Hellman key exchange does, it enables Alice and Bob to share a certain number, the key, which they can use in cryptographic schemes. But they're not able in this way exactly for one to send a secret message to the other. That is, if Alice wants to send Bob a message, this Diffie-Hellman key exchange does not allow her to do it. Diffie-Hellman key exchange allows Alice and Bob to share a key over a public communications network in which everyone can intercept and steal everyone else's message. But it does not enable Alice to send a message to Bob or Bob to send a message to Alice. So how can we do that? Right? Again, everything assumes that every communication back and forth can be intercepted by the enemy and read. There's no secret method of communication, right? Everything is read. There's no secret method of communication. But Alice still wants to send a message to Bob. And how can she do it? So there are two basic ways we're going to develop what is called a public key crypto system. So this is to communicate messages securely. That's what we want to do. Communicate a message securely. And we're going to look at two systems. One is called the El Gamal system, the El Gamal public crypto system. And the second is called RSA. The letters came from the names of the people who discovered it. Rivest, Shamir, and Edelman. The story is, I don't know if it's true, that Rivest and Shamir were professors at MIT working on this problem. And Edelman was a graduate student who used to hang around the coffee room in the MIT computer science department. And Rivest and Shamir would try to come up with some cryptographic scheme, and they would be talking about it in the coffee room. And Edelman would try to break it. And so he wasn't coming up with the scheme exactly, but he was involved in all the discussions and trying to break it. And when they finally did come up with something, Rivest and Shamir, they added Edelman's name to it. So it became RSA. And this became one of the most valuable patents in cryptography. That is, this communication scheme is patented. It's used everywhere now. You can't buy, when you buy something on Amazon, you type in your credit card number, it is encrypted using RSA. And these three guys made a lot of money because anyone who wanted to use their system had to pay them for the use of their patents. And eventually, after a certain number of years, your patent expires. But for a long time, it was a lucrative thing for Rivest, Shamir, and Edelman. We're going to talk about this maybe tomorrow or Wednesday. Today, I want to talk about the El Gamal public key crypto system. So now we're not trying to come up with a number that Alice and Bob share. Now we want to come up a way for Alice to actually send Bob a message. And remember, every message is a number, right? You take your message, every letter, every punctuation symbol, get some numerical equivalent, you string it all together, your message is converted to a number. That part is trivial, right? So how can Alice, so here's Alice, here's Bob, here's some message, M, that Alice wants to encrypt. She does something, and she sends whatever that something is She sends it to Bob, and of course, Eve intercepts it and knows what Alice is sending, but it's encrypted, right? And how can Alice do this in such a way that Bob can decrypt the message, but Eve can't? Okay, so let me start with a clean piece of paper. So this is the El Gamal crypto system. So what does Alice do? So what is given? What is public knowledge? Everyone knows this. Alice, Bob, Eve, and everyone. There's a prime P, and there's a primitive root G. So everybody knows these, all right? So Alice chooses a secret number A, and she computes the number capital A, so this should look familiar, which is G to the A mod P. And here is Bob, and this is Eve listening in. And Bob and Alice sends this number capital A to Bob. So Eve intercepts and knows the number capital A. Okay. Let's say it's actually Bob who wants to send a message to Alice. Right? So Bob has some message M. Right? It's a number. That's the message between 2 and P. So Bob chooses a secret number K. And this is what he does. Bob is going to compute two numbers. So Bob computes two numbers, C1 and C2. So C1 is, you take the primitive root G, he raises it to a secret number K mod P. That's his C1. And then he computes C2, and C2 is going to be his message M times capital A to the K mod P. All right. So this is more complicated than Diffie-Hellman. In Diffie-Hellman, Alice chose a number little a and Bob chose a number little b. Here, Alice again chooses a number a, but little a. Bob chooses a number, but we're calling it k this time, because this is going to be an ephemeral key. He's not going to use it very often. It's ephemeral, but it doesn't matter. Bob chooses a number little k, and just as he did in the Diffie-Hellman, he computes G to the K mod P and calls that C1. But then he takes his message, that's a number, and he multiplies it by capital A to the K, where capital A is the number that Alice sent him. So these are the two numbers, C1 and C2, right? And what Bob sends to Alice is the pair C1, C2, right? So what Alice sends to Bob is this number A. What Bob sends to Alice is this pair C1. And the first thing to check is, this is a claim, Alice can decrypt C1, C2 to obtain the message M that Bob wanted to send to her, right? Again, the whole point is Bob has a message, it's the number M, he wants to send to Alice. He's going to send this pair of numbers C1, C2, and the claim is that from C1, C2, Alice can figure out what M is. Okay? So this is what Alice does. What Alice does. First, she computes C1, that's the first number she got from Bob, C1 raised to the power A mod P, and we call that X. So only Alice knows her secret number, little a. She takes C1 to the power A and calls that X. 2, Alice computes X inverse. That is, X inverse is a number such that X times X inverse is congruent to 1 mod P. Right? Every non-zero number mod P has an inverse mod P. Alice can compute X inverse. Next, this is the third step. Alice multiplies C2 by X inverse and looks at it as mod P. So again, Bob sends the numbers C1 and C2 to Alice. Alice also knows her secret number, little a. So first she takes the first number Bob sent her, C1, raises it to the power A, call that X. Then she finds the inverse of X mod P. That can be done. Then she computes C2, that's the second number that Bob sent her, X inverse. So what is C2 X inverse mod P? So T2 X inverse, what is C2? That's M, A to the K mod P times X inverse. What is that? That's M. What is capital A? A is G to the A to the K times X inverse. That's M, G to the AK times X inverse. What is X? X is C1 to the A. This is M, G to the AK. X is C1 to the A. C1 is G to the K to the A mod P inverse. This is M, G to the AK, G to the minus AK. These cancel. You just get M mod P. So this is the miraculous calculation. From C1 and C2, Alice recovers the message M. Right. Now, this, I admit, I don't know if Diffie-Hellman was easy, but this is harder than Diffie-Hellman, but we're also trying to do something more complicated. So let me work through an example of the El Gamal crypto system step by step. And maybe that, again, it still is hard to understand, but it makes it easier to go back when you're studying and look at the theoretical description and then look at the example. Okay. So this is an example. This is example 2 on page 69. So we have the prime P equal 467, and the primitive root, it turns out that 2 is a primitive root for the prime 467. And suppose Alex, her secret number A, let's say it's equal to 153. So capital A will be 2 to the 153rd power mod 467. And if you do the calculation, this turns out to be 224. So that's the number capital A that Alice sends to Bob. So Bob gets this number. All he gets is the number 224. Suppose Bob's message that he wants to send is, it's a number between 2 and P, say it's 331. So Bob wants to send the message 331 to Alice, and Eve, intercepting everything going back and forth, can't figure out that the number is 331. So Bob chooses the secret ephemeral key, 197, and computes the number C1, which is 2 to the 197 modulo the prime 467, which turns out to be 87. So in the pair that Bob is sending to Alice, C1 is 87. And what is the number C2? C2 is the message times A to the K. This is the message 331 times A, 224 to the exponent 197. And this turns out to be 57 modulo 467. So the number Bob is sending to Alice, the second number, is 57. So what Bob sends to Alice is this pair, 87, 57. So how can Alice obtain the number 331 from the pair of numbers 87 and 57? Right? So what does Alice do? First, Alice computes X. X is C1 to the A mod P. C1 is the number everyone knows, 87, but a raised to Alice's secret number, 153, modulo 467, and yeah, 87 to the 150, sorry, yeah, 87 to the 153rd power. This turns out to be 367 mod 467. This is just a computer calculation. So Alice takes the first number she got from Bob, 87, raises it to her secret power and reduces it modulo the prime 467, and she gets the number 367. Then it turns out X inverse is just 14 mod 467. 307 times 14 is going to be congruent to 1 modulo 467. And the very last step is to calculate. Alice computes the number she got, the second number she got from Bob, C2, times X inverse. X inverse is 14. The second number from Bob is 57. So we're calculating 14 times 57 mod 467. And if you multiply these numbers, divide by 467, the remainder, lo and behold, is 331. So Alice has recovered the message Bob wanted to send her. Okay. All right. Okay. Well, that's the system. That's it. So in the homework, there will be some examples, exercises, implementing both Diffie-Hellman and El-Gamal. And that's very important. Okay. Any questions at this point? Now, when we go further.
Hi, Professor. I have one question.
Yes, go ahead.
Yeah, in the previous one, how Alice and Bob knows they have to compute z to the power a for like a uppercase a to the power b or uppercase b to the power a. Why not like a times a or b times a?
What they know, no, what Alice and Bob and Eve and everybody in the universe knows is what is the Diffie-Hellman algorithm.
Oh, okay, so everyone knows that
they have capital A to the little b or capital B. This is prescribed. They're not guessing this. There's no guessing. They're not being smart. They don't have to be smart. They just have to follow orders.
Okay.
So, Alice chooses her secret number, little a. Bob in Diffie-Hellman, Bob chooses his secret number, little b. They exchange numbers, capital A and capital B. And from those two numbers, each can compute a third number, which is the same for the two of them. And that's the share.
So that's the formula they have to follow.
Yes, that's given. They don't have to invent this.
Okay.
Diffie and Hellman thought it up and everyone uses it.
Okay. And in this case, C1 and C2, only one person will send C1, C2? Not both?
Bob, right. So Bob sends C1 and C2 to Alice. And that's how he has encrypted his message M into this pair of numbers. He sends that pair of numbers, C1, C2. Alice receives them And from that pair of numbers, she's able, without doing any thinking at all, it's automatic, to recover the secret message M.
Okay.
Right?
So this
No one's
formula
allowed
is
to think.
also given
No
by.
one's allowed to think in this process. No one is allowed to be creative. You follow
Okay.
orders, you follow the cryptographic scheme, or nothing works.
Okay. Thank you.
Yes. Okay. Now, for further work in cryptography, we need to know a little bit more about number theory and a little bit about what are called groups. So let's see. So we talked about Diffie-Hellman. We talked about El-Gamal. And I'm just going to say a few words about groups, and I'll talk about this more tomorrow. So this is what in mathematics and algebra is called group theory. So a group is a set with a binary operation. It's often written as multiplication. It's often written as addition. But I'll call it star. And it has the following properties. So it's associative. So A times B times C is the same as A times B times C. So for example, if you think of, let's see, the non-zero real numbers with ordinary multiplication, or FP star, the non-zero congruence class is mod P, these properties are satisfied, right? 2 times 3 times 4 is 6 times 4, or 24. 2 times 3 times 4 is 2 times 12, or 24. It's the same thing. So multiplication is associative. There's also an identity element. E. E times A and A times E is always A. So for ordinary multiplication, it's 1. 1 times 7 or 7 times 1 is 7. It's commutative. We're only going to look at commutative groups. A times B is B times A, right? 2 times 3 is 6, and 3 times 2 is 6. And you have inverses. So given A, there exists an element, I'll call it A inverse, such that A times A inverse and A inverse times A is equal to the identity. So in the reals, if A is 3, A inverse is a third. 3 times a third, and the third times 3, they're equal to 1. So whenever you have a set of objects with some binary operation, you can add them or multiply them or do something to them. That's associative, commutative, there's an identity, and every element has an inverse. That's what's called a group. Right? And if you look at FP, that's an additive group. Under addition, that's an additive group. FP star, the non-zero congruence class, is mod P. Is a multiplicative group if P is a prime. So there are lots of examples of groups. If A star B is not B star A for all A and B, then we have a sort of non-commutative group. That rule doesn't always have to happen. So for example, if you take G to be the set of all matrices A, B, C, D, where, like, let's say the determinant AD minus BC is 1, this is a multiplicative group. So matrix multiplication is associative. The identity is just the 1, 0, 0, 1 matrix. And A, B, C, D, the inverse is D minus B minus CA, I think, if you do matrix multiplication, given that AD minus BC is 1. So the set of 2 by 2 matrices is an example of a multiplicative group. But if I take, for example, 1, 2, 3, 4 times, I don't know, 2 minus 1, 0, 1. Now you have to know matrix multiplication. This is 2 minus 2. This is 0, 2, 2, 4. If I multiply in the opposite order, let's see what I get. I get 2, 4, 2, 2. They're different. So here I just reverse the order of multiplication. I get different matrices. So this is a non-commutative group. Very important group. And, well, this is a whole subject. I don't want to do any more today, actually, but I'll talk about this more tomorrow. The thing to concentrate on from today, because it definitely will be on the midterm, is Diffie-Hellman, key exchange, and El-Gamal, public key crypto system. So you really need to spend time studying these. It's fundamentally important.
Is Chinese remainder theorem is going to come?
Yes.
Okay.
Yes, a few pages later in the text. Just to make things relatively easy in the summer, I'm trying to follow the text carefully, one topic after another. But you'll see we'll have the Chinese remainder theorem tomorrow.
Okay. Because I have problem understanding the simultaneous equations.
Mm-hmm.
How to solve like for 2, 3 equation.
Right. Well,
So
solving equations is something you have to know from pre-calculus.
no, the Chinese remainder theorem, like it's a big number. It's like x equal this, and then x equal this, and then x some common solution for 3.
Yeah. No. I mean, it would be find x such that maybe x is congruent to 3 mod 17, and x is congruent to minus 4 modulo 11. Okay?
No, it's a bigger number. If modulo is very big number.
Well, big number or small number. If it's a big number, you use a computer or a calculator.
Oh, okay. A small number is fine. I understand. Like less than that, all the solutions we have to check, right?
Yes. Well, no. Well, I mean, there are more efficient ways than trying every solution, but yes. But I'll show you tomorrow when we do the Chinese remainder.
Okay. Okay. The equation one. Okay.
Yeah.
Okay. Thank you.
Any other questions? All right. Then we are done for the day.
Thank you so much.
All right. Back tomorrow at 11. Bye all.
Bye.